So we will see today what are the different types of common physical nonlinearities, okay, or the general classification, like in what form nonlinearities come in a real system. Okay, now majorly they are qualified as two types. First one is incidental nonlinearities, and second one is intentional nonlinearities. Now intentional are ones that are introduced by the control designer, okay, and incidental are ones that are existing naturally, okay, existing naturally in the system. They may be by design also, but you don't do it deliberately, okay. There is some, let's say there is, you have designed a system like your pointer system that we considered yesterday. It was designed such that you won't exceed more than 10 pointers, right? So it is by design capped or saturated at 10 pointer, but it is naturally occurring, we can say that, okay. It is not intentional that you are limited at 10 pointers, okay. So it is incidental nonlinearity, and intentional nonlinearities are the ones that are introduced by the control engineer. See, these are deliberately inserted to modify the system characteristics, okay. So basically, if you put an intentional nonlinearity, it is kind of a device. If that device has a nonlinearity, you are simply making the system loop a nonlinear system. Yes, even if the system is linear and you are putting a nonlinear controller, let's say, your controlled system, the closed loop system, will be a nonlinear system. Okay, so that is called as intentional nonlinearity. And incidental nonlinearities has these types. So first one is saturation. We will see them in details, okay, with the graphs, and there are even subtypes of them. So first one is saturation, second is dead zone, third is the friction or Coulomb friction, and the last one is backlash. Okay, oftentimes you are confused with backlash and dead zone. Okay, but we will see what is the difference between them. Also, there are different names for this backlash. You will see. You will see. We have not discussed hysteresis here yet. Okay, but hysteresis is a type of. It can be classified in this also. Okay. So first one is saturation. See, uh, so the saturation. You know what is saturation? Like there is a limit to the input. Okay, there is a value for input for which the system gives maximum output. Okay, beyond that the system will not will fail to produce any more output. Okay, so see the components such as amplifiers have output proportional to input in a limited range of input signals. Okay, as you can consider this, let's say that you have some 2 to 3 millivolt input to a system, and it is giving you gain of 1000. Okay, so if you put 3 millivolt, you are getting 3 volts output. Yeah, if you give it 5 millivolt, you will have output as 5 volts, but there is a limit to that, right? Now if you give input to that amplifier, let's say 1 volt, are you able to get 1000 volts as output? You should get, in theory you should get, but you don't get it, right? The amplifier has some limits, so that limit is basically called as saturation. Okay, it may have limit as, let's say, plus minus 10 volt. So beyond 10 volt it will fail to do the amplification. Okay, so that saturation can be translated into the input terms as let's say 10 volt by 1000, it is 10 millivolt. So beyond 10 millivolt, it will not be able to amplify those signals. It will amplify them, but the output will be 10 volt beyond that 10 millivolt. Okay. So see, though the changeover from one range to another is gradual, it is sufficiently accurate in most cases to approximate the saturation phenomena by straight line segments as shown. We'll see. See here. So the actual characteristic of the system are shown by the dotted line. And as you can see, as it goes towards the limit, 10 volt in our case, as it goes to the limit, this becomes flat. Okay, so no amount of input any amount of input that you increase here, you will get the output as this same point. Okay, so that way you can say that this is a saturation function. You know what is saturation function? Yeah. Now, if you just consider this, the slope of this graph is nothing but the gain of that amplifier or gain of that system. Okay, and this is approximation, linear approximation can be done in this range only. See, from this point to this point. So you can say that in this box, if we draw a box around this, it is linear. Also, you can see that around 0, it is linear. So our general operating point for the systems are considered as 0, near 0. So near 0, you can see that the gain is linear. So this nonlinearity does not have that much, we don't have that much problem with this, as long as we stay within limits. As long as, let's say, we stay within these two lines. Okay, let's say +5 and -5 volt. Just that we have the limit as 10 volt, but we keep ourselves such that the output is between the range -5 to +5 volt, so that we will get a linear output for the given input. Okay, so this is saturation, first type of nonlinearity. Now second one is friction. This is the friction is also sub-classified into three parts. The first one is viscous friction, second is Coulomb friction, and third is stiction. Okay, what each of them are is written here. As you can see here, viscous friction is proportional to the relative velocity of sliding surface. Okay, now this viscous friction is the friction that we denote by the notation B. In case of our mass spring damper systems, it is the viscous friction. Okay, and viscous friction is a kind of a linear relation between the force applied and the velocity of that two moving surfaces. Okay, relative velocity means one surface is going, let's say, leftward by 5 meters per second. Another surface is going rightwards by 10 meters per second. So the relative velocity will be 5 meters per second. Okay, on that relative velocity, it is acting viscous friction. This is the most common thing. Now, the nonlinearities are added because of Coulomb friction and stiction. Okay, so what is Coulomb friction? It is opposing to the relative motion, the same as viscous friction, but there is this Coulomb friction is due to the molecules and their dynamics. Okay, Coulomb friction, and there is a stiction. So stiction is, you can say, you can call it as activation energy or the initial energy required to move the object. Okay, like if that object is stationary, how do you start its motion? Means there will be the force required for keeping it in motion will be less than the force required for starting it in the motion. You understand this? Yeah. To start something, you need more energy, and you require less energy to keep it going. Okay, so that is called as stiction or initial energy. We can say initial force applied by that uh, the friction. Okay, initial force applied by the friction I'm talking about overall friction. Okay, so these three components are part of the friction that we call generally. Okay, now see, the stiction is always greater than Coulomb friction. Coulomb friction is very, very small, and stiction gradually decreases with velocity and changes over to Coulomb friction. Okay, so this stiction is predominant in the stationary part, that is force 0 or velocity 0. If the velocity is 0, then the stiction is more. As velocity grows, this is very less. Okay, But Coulomb friction is opposite. The Coulomb friction increases as velocity increases. Okay. See, the characteristics are shown. We'll see that figure. At very high speeds, frictional force will become proportional to the square and cube of speed. Okay. This how this is, we'll see. So this is viscous friction. As I said, this is very linear relation. So the more velocity the object is moving with, the more force it will exert. Okay, simple. And these are Stickson and Coulomb friction both in the same graph. And see, yeah, okay. So these are ideal, and yeah, you can consider this first. As I said, this Stickson is very high in the initial part. Okay, so near zero it is very high, and as velocity goes on increasing, it reduces to the value that is Coulomb friction. Okay, so this Coulomb friction will always be there, although these both of these values are very less compared to this, but they are there. So there is a nonlinear kind of relation here. As you can see, a complete switch over is happening at velocity is equal to zero. Okay, these are ideal characteristics of Coulomb friction, where if this is not visible maybe, but as you can see here, it is not drawn here. It is kind of impulse. Okay, so this friction is impulsive kind of thing. Okay, so it will have a very high amount here, and then again it will go to the Coulomb friction side. So this basically you reduce this part, increases height. Impulse, you know what is impulse. Okay, so the next one is adding all these three frictions. Okay, if you add this graph and A and B graph, you will have this. Okay, where this is the baseline. This is the baseline. As you can see, if you go from velocity minus to some plus point, this you will have a graph. Okay, this is just for representation, or you can consider this as very zoomed in version. But this is a Coulomb friction, the amount of force that will be required minimum. Okay, force that is exerted by the object. This is the minimum force that is exerted. Okay, and this is the friction. And this can be I mean, this can see the dotted line is you can consider as the ideal relation. Okay, the way that it can be modeled into three linear parts, right? First one is this from minus let's say minus 0.1 to minus some point. So this is linear from this point 0.1 to higher limit. It is linear. Just this minus zero point 0.1 to plus zero point 0.1, it is not linear. It is a straight line, like very high gain you can consider. Okay, so this is second nonlinearity, that is friction. Third one is backlash. Okay, now this backlash is also called as hysteresis. Okay, now hysteresis is if you know this hysteresis phenomena, it is that you get different values if you increase the input and decrease the input. Like if you go on increasing the input from 0 volt to 10 volt, let's say, you will have a you will have a one characteristic. You plot that characteristics, and then again you try to reduce that voltage from 10 volt to 0 volt and plot the second characteristic graph. So those two graphs should overlap, but they don't overlap generally. Okay, and that phenomena is called as hysteresis. So this hysteresis is you can consider mechanical systems such as gears. So gears have this backlash. Okay. Now, when this backlash error happens, is that as you can consider this. See, this is one teeth, only one teeth and slot here. Okay. Yeah. Or you can, yeah. This is also a slot I am saying, but this is also a teeth. This B1, B2 are nothing but the two teeth of the another gear. Okay. This is driving gear, you can say, and this is the driven gear. And as you can see, this A, if it is moving with angle theta I, okay, this B by 2 and this B by 2 are basically small b, will be that error between uploading and downloading. Let's say this is moving clockwise like this. This is anti-clockwise. So it is moving anti-clockwise. Then this A will touch this B1 to drive this gear. Okay, there will be the gap of B. Now, if you start moving it in clockwise direction, this gear has to move from this edge to this edge. So that B distance translated into some angular measurement, it will be some translated, or we consider this theta as some distance. Okay, because we are considering very small dynamics. So that theta is the backlash error you can consider. Okay, so the graph is written or drawn here, as you can see. If you go on uploading, see this PQRSTU is the way that this moves. Okay, and as you can see, the uploading graph and downloading graph are not overlapping. Ideally, both of them, this S and R, will overlap. This T and U will overlap as one single point. Okay, but in reality they don't. So this is called as backlash nonlinearity. See, in servo system, gear backlash may cause sustained oscillations or chattering phenomenon of the system, and the system may even turn unstable for large backlash. Okay, so because of this, so this is basically a system exhibiting two different dynamics, right? So how do you design a controller for that? And even if you design a controller for, let's say, this motion, U, Q, R, okay, then it will not work for SPT that way. Okay, so what works for up, going up will not work for coming down. Yeah. So this may make this poses some problem in the system design. Okay, so this was the third non-linearity, that is backlash error or backlash non-linearity. It is called. The next one is dead zone. Now this dead zone may sound similar to backlash, but yeah, you can call it that also. You can categorize it as that. But dead zone is basically the region where you provide input, but you see no change in the output. That is called as dead zone. Okay, you are providing let's say 2 hours a week, but you are seeing no change in the pointer. Then you turn up that to 5 hours a week study, and you start to see the change in the pointer as, let's say, 0.1 pointer changed with 5 hours a week. But for 2 hours, it should have been relative, right? It should have been relative. You should have got 0.04 pointer change, but you don't get. Okay, so that range, that minimum input, is called as dead zone. Okay, so there is a minimum effort that you should give in for that system to start working. So this is called as dead zone. See here, here also it can be considered. So this B by 2 plus minus B by 2, this region, as you can see, the gear from gear A touching this teeth A, it moves from B1 to B2. But this gear, the driven gear, does not move in that region. So that is called as the dead zone. Okay. So this is just explained. That one is explained here. So in addition to above example, you can consider a DC motor. If you have done some projects, you know this, that if you apply a 3 volt to a DC motor of 12 volt rating, okay, 3 volt, let's say you apply. So you are not getting the RPM divided by 4. If, let's say, for a 12 volt, you should get 3000 RPM, or let's say 4000 RPM for the sake of easy calculations. Okay, so for 12 volt, it is rated that you will get 4000 RPM, but you don't get 1000 RPM for 3 volt. For if you provide 3 volt to that motor, it won't even move. Okay, so that is a dead zone, 3 volt. So you turn up that voltage, let's say 4 volt, 5 volt. So at 5 volt, the motor will start moving. Okay, and it will start moving at minimum, let's say 1000 rpm, and from that 1000 to 4000 it is linear range, somewhat linear. But in the region 0 to 5 volt, the motor did not move at all. Okay, did not spin at all. Now this is true for the reverse also. If you apply, if you just take out the terminals, positive negative terminals, and reverse them, the motor will move in anti-clockwise or clockwise, if the opposite direction of the earlier one. Okay, but it will not move for 0 to minus 5 volt. It will move to 4000 rpm for 12 volt, but it will not move even for minus 5 volt. You understand this? So the dead zone for this motor, this particular motor, is minus 5 volt to plus 5 volt. Okay, so plus minus 5 volt you can call as the dead zone. Now see, it is insensitive, a small input voltage signal. That is a dead zone, you can consider. All right, see this, this b by 2, this b by 2, where this b will be what, 5 volt in our case, but this is in theta, so this is for the gearbox. But if we want to translate into our dc motor example, you can consider this as the input voltage, and this is the rpm. And in input voltage, this you can write as minus 5 volt plus 5 volt, and this is linear. Okay, so the slope will be what, 5000, 4000 divided by 12, so whatever that is. Okay, 1 by 3, 100 by 3 rpm per volt, something of that kind. Okay, so that will be the slope of this graph. So this is the Deadzone nonlinearity, the fourth type of nonlinearity. Okay, and the last one, that is an intentional nonlinearity that we introduce, is a relay. Now if you do you know what are relays? You are electrical students, right? So I hope that you have studied what are the different switching types and switches and relays. Yeah. What is a relay? Can you describe the function of a relay? Anyone? It is not explained here. Don't read the slides and expect that you will get the answer. I'm asking based on your previous knowledge, based on your degree that you have chosen to do, electrical engineering. You must have studied what are relays, or if it
So
is,
it is used as a switch
yeah,
to
very
on
nice.
or off the
Mm.
circuit.
How is it different from a manual switch? A manual switch on the switchboard. How
So
a
it
relay is
is
different?
so
Hmm.
it is operated by it is like electrical signal is given, and like manually we have to press the on and off button
Hmm.
to control the example fan or like
Yeah.
light. But
Okay.
in the relay,
Hmm.
yes, you got it. Yeah.
Yeah, yeah. So the basic function of relay is that you convert a signal to power. Okay, signal is generally in low voltage or low current terms, right? The electrical signal, and power is in let's say 230 volt, 2 ampere, or even 12 volt, 2 ampere, 1 ampere, that kind of. So you have to convert a signal into power, so that is an amplifier. So this relay is basically an amplifier, but it is a digital amplifier. Okay, so if you give let's say positive voltage to a relay, it will connect one terminal, let's say anode terminal, to the normally the middle leg. Okay, and if you don't give it a positive voltage, then the relay will connect the normally connected voltage to the middle leg. Okay, so this is the basic function of a common place relay. Now as you know that if you give let's say positive input to the relay, you have a high output, or fan on or light on. And if you give low input to the relay, let's say 2.5 volt or less than 2.5 volt, 1 volt, 1.5 volt, then your relay will give output as off. Your bulb will be off. Okay, so basically even if you give a digital analog input to that relay, there will be a threshold, and depending on that threshold, it will give output as on or off. Okay, so where it is used, it is generally used in on off controller. The most used it was most used controller back in the day, but it is no longer. Nowadays PID is very commonplace, but still in the cases like home automation and those things, you just need on and off, right? So a relay can be used there. See, nowadays in place of electromechanical relays, the ones that make sound tuck tuck, instead of those, SCR switching is employed. SCR, you know this, you may have studied in power electronics. So that is employed. Okay, silicon controlled rectifier. In that you don't make any tuck tuck sound. That means there are no moving parts there. Okay, so the relay characteristics are near ideal, but in place of electromechanical relay, they are somewhat uh, uh, similar to uh, let's say stiction. Okay, it is kind of that, like you will have impulse near the switching point. But see here, so is an ideal relay characteristic. As you can see, input you can give in analog range, but output you will get in either this positive or negative voltage. Okay, this may be scaled. You may say that, sir, it does not give negative 0 volt or negative minus 230 volt. Yeah, this can be scaled. Okay, so the output range, you may consider this as 0 volt and this as 230 volt. Okay, or the other way around, like for low inputs you will have plus output, and for high input you will have the negative output, something like that. But this is the general characteristic that a relay has. Okay, ideal relay has. Now the second one is the relay with the dead zone. Okay, now here also in case of relay, like I said, the if you give input, let's say 1.5 volt, and you change that 1.5 volt to 1.4 volt. Okay, even if near the switching, let's say 2.5 is your switching threshold at which your relay either makes on or off, and if you give 2.4 volt or even 2.6 volts, it will not switch. So this is the 2.4 to 2.6 range in which the relay will not act. Okay, so that is called as dead zone. But this characteristic means real relays don't exhibit these characteristics, but these characteristics. So this relay with pure hysteresis is what an on-off with dead time or dead zone, maybe, yes, dead zone is called as. Means this refers to this graph, not this. Okay, now in this you consider, see, now it will go to 2.6 volt, then it will be switched on. It will remain on even if you go below 2.4 volt, and once you reach the 2.4 volt and go below that, then it will be switched off. Okay, so this is the application that we are desired that we desire when we design a on-off controller with dead band. Okay, so that is a hysteresis that we are concerned about, not the dead zone that is given here. Okay, and this is a kind of a very practical relay where it will have dead zone also and hysteresis also. Okay, now it is represented in this way. It can be either represented with another way, like this going up and nothing happening in the zero region, that way also. Okay, so these are some characteristics. As you can see, different types of non-linearities are combined here. Like relay's characteristic is this only. Relay is combined with dead zone. Relay is combined with pure hysteresis. And relay combined with dead zone as well as hysteresis. So multiple types of non-linearities may occur in the system. Okay. And these are the common physical nonlinearities. We will see phase plane method tomorrow. Is there any doubt in this? See, we have seen these 5 nonlinearities, and these are most common physical nonlinearities. Okay. Also, now think about this. If you have this function, how can you express this in mathematics? How can you write an input-output relation for this graph? You will require a multi-valued function, right? So that multi-valued function is basically a non-linear function. You cannot find a state model of that system or a transfer function of this system. You will have 3 transfer functions, yeah, depending on the region. If input is in this range, then use this transfer function. If input is in this range, then use this transfer function. If input is within the operating range, then use this output by input is equal to gain. Okay, so it will be a multi-valued function. This is the piecewise linearization that we have done. Is this understood? If there are any doubts, ask.